To learn more about earning college credits with study hall courses, visit gostudyhall.com or click the link in the description. If you have a randomly shuffled deck of 52 playing cards and you're trying to find, say, the Queen of Hearts, you gotta rely on magic. Dang it. Sure, you could try fanning them out or flipping cards one at a time, but there's no rhyme or reason to find the queen that you're looking for. But if your deck is neatly organized from 2 to ace in each suit, your search will go way faster. You can go to the hearts, skip past the low numbers, and find the Queen of Hearts. No problem. My point is, you don't have to be a magician or mathematician to realize that a sorted deck of cards is way easier for our brains to process than an unsorted deck. We humans love a pattern. And the same logic applies to computers that are processing lots of data. A sorted array list is much faster to look through than an unsorted one. So, let's get into the magic and math of how to sort data with a program, because we want our code to run as smoothly as possible. I don't know what I was looking for with this, but hi, I am the unmagical Sabrina Cruz, and this is Study Hall, code and programming for beginners. Can't wear the hat the whole episode. Anyway, earlier in this series, we learned how to program ArrayLists in Java, which are collections of other objects. These ArrayLists, or lists for short, can contain thousands or millions of elements that we can access later. But not all lists are created equal. Usually, when we collect lots of data, especially random user inputs, we have an unsorted list. There's nothing fundamentally wrong about an unsorted list, but searching through it can take a lot of time and processing power. I think the technical term for this is it's freaking annoying. To solve this problem and create much less annoying sorted lists, computer scientists have designed all kinds of sorting algorithms. Remember that an algorithm is a set of step-by-step instructions that can be implemented in any programming language. So, sorting algorithms are basically just different organizing strategies, and each one has strengths and weaknesses depending on the data you're trying to sort. To understand two of the simplest sorting algorithms, let's go back to our card deck from earlier, but this time we'll have a little competition between friends. Suppose two people are given 13 playing cards in a shuffled stack. Each person's goal is to sort their stack of cards the fastest, from least to greatest value, ace is high. So that would be 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king, and ace. One player goes the super chaotic route. They throw their cards down randomly again and again and hope that they land in the correct order. Now, they might get lucky if they repeat this process enough, but it would probably take an impossibly long amount of time. In sorting algorithm terms, this strategy is called random sort, or monkey sort, maybe in reference to the whole infinite monkeys with infinite typewriters could replicate Shakespeare, so like with enough attempts, you'll eventually get there. Theoretically. It's kind of unfair to monkeys though, since they have pattern recognition and would find sorting way easier than Shakespeare. But I digress. The second player has more of a system. They lay out their cards in a row and systematically compare them. Specifically, they compare the cards in the leftmost two positions and swap them if needed so that the second card has the greater value. Then they compare the cards in the second and third positions, making sure the higher card ends up in the third position. As they move down the line of cards, making comparisons and swaps, the higher value cards will move to the right, and after a few passes through the stack, they'll be done. This slightly more methodical strategy, which gets you a guaranteed result, is called a bubble sort algorithm, because the greater value cards, or whatever you're sorting, gradually float like bubbles to one end of the list. Bubble sort isn't the most glamorous algorithm out there, but it's one of the simplest ways to sort a list and can be applied to many different problems. For example, instead of a human following an algorithm to sort cards by their value, let's tell a computer to sort a list of names in alphabetical order. The bubble sort algorithm often looks really short as pseudocode, but the difficulty is in the details when you actually have to code something in Java. Remember, computers don't know anything we don't tell them, and they're mostly good at, well, computing with numbers, so they definitely don't know their ABCs. To implement bubble sort, we need our computer to determine whether one name should alphabetically go right of or later than the next name in our list. We're working with the string data type here, so we can use one of two string comparison methods that are built into Java. The .equals method tells us if two strings hold the same value and outputs a true or false Boolean value. In other words, it's checking whether two names are the same, and that won't help us when we're sorting our list alphabetically. alphabetically. On the other hand, the .compareTo method takes corresponding characters in two strings and compares their ASCII values. ASCII, or the American Standard Code for Information Interchange, is a common encoding method that converts human-readable terms to computer-readable terms. ASCII maps letters, numbers, and symbols to specific numerical values that are then converted to binary. It's easiest to explain how this method works through an example, so let's use .compareTo with the names Aaron and Cecilia. To call the method, we need to create the two string variables we want to compare: first name, which we'll set to Aaron, and second name, which we'll set to Cecilia. The .compareTo method compares the ASCII values of the first characters in both strings, which are A and C. The ASCII value of capital C in decimal is 67, and capital A is 65. If we write first name .compareTo second name, our program will take the decimal value of A in the first name and subtract the decimal value of the C in the second name. That's 65 minus 67, which is -2. So basically, these ASCII values give the computer a numerical way to understand alphabetical order. If second name is later in the alphabet than first name, you'll get a negative number. Cecilia is alphabetically later than Aaron, so we got -2. All that is to say, to implement a bubble sort algorithm on a list of names, we can use the .compareTo method to do a bunch of comparisons one after another, which is where the for loop shines. Each pass through the list pushes the name with the character with the largest ASCII value to the end. So after two passes through the list, the rightmost two names are sorted and will never move again, and so on until the list is completely sorted. To see bubble sort in action, let's take a look at a complete implementation in Java, for loops and all. We'll start by creating a new method for bubble sort that takes in our list of names. We also need a temporary string that we can set to different names from our list as we loop through it, and the length of the list. The outer for loop can iterate as many times as there are names in our list. This way we can make sure that the whole list gets sorted even if it's completely backwards, since we can only bubble one name to the end during each loop. And the inner for loop is actually doing the bubble sort, comparing the name at the current index to the following name and swapping the order or not. If we get a negative number from the .compareTo method, the two names are already in alphabetical order and there's no swapping needed. But if we get a positive number, we should swap the two names and move to the next pair. If we try to do both of those things in one for loop, it would be extra complicated to keep track of where we are in the list, because we don't always want to make a swap. And that temporary string is key to making a swap. Unlike swapping two playing cards on a table, we can't swap two names in the list at the same time. Instead, think of it like two cars trading parking spaces with only one driver. You need a third empty space to temporarily park one car as you move the other. We can basically move a name out of the list by setting it to the temp variable, reassign a new name to its old index, and then move the name back into the list at a new index. Eventually, after many loops of comparing and swapping and bubbling names, we'll end up with a sorted alphabetical list. When we talk about the performance of an algorithm or program, the first thing we talk about is whether it'll get the job done at all. But after that, we also care about time complexity, or how much computational time our code needs. Programmers describe time complexity with something called Big O notation. In Big O notation, we say that the performance of bubble sort is order n squared. The O is an abbreviation for the order of complexity, and n represents the number of items in our list or dataset. Order n squared describes the worst case scenario for a bubble sort implementation. If the list was perfectly backwards, it would take n squared comparisons to complete the sort. Every single list element would need to be compared to every other element. So if there were 100 elements, that would be 10,000 comparisons. So bubble sort is relatively easy to learn and implement, and it will do the trick for short lists of data or partial sorting, but it's not necessarily the best way to handle every problem, especially huge lists. Multiple algorithms can often do the same task, but one algorithm may perform better than others under certain circumstances. circumstances because it's faster or simpler or easier to implement in a specific programming language. And programmers can weigh their strengths and weaknesses using tools like Big O notation. Many of the problems we tackle with computer science involve tons of data, so sorting data is an incredibly important skill as a programmer. And while you might be able to organize a physical deck of cards no problem, it's a totally different challenge to make a computer sort cards, or the names of everyone that live in your town, or radioactive mice data. Your brain can go by vibes and switch strategies on a whim, but you have to tell a computer exactly how to make each logical decision. The upside is that a computer can execute your instructions extremely quickly, so the time it takes you to tell the computer instructions can be quickly made up for in the time saved doing the actual sorting. Bubble sort is one of the most basic sorting algorithms out there, so it's a great way to start doing some magic with code. If you're enjoying Study Hall Code and Programming for Beginners and are interested in taking an online course and earning college credit, check out gostudyhall.com or click on the button to learn more. Thanks for watching, and see you next time.